Right. I'm sure we have a lot of questions. Cynthia, I wanted to ask you, you said that your Wello wheels last 3 to 5 years, but potentially longer, but what happens, how do you recycle them?
So they definitely can be recycled, but keep in mind we're working in extremely rural and remote communities that don't have readily available recycling at hand. What ends up happening is that people reuse them. So we've seen water wheels turned into feeding troughs and water troughs for animals, kitchen gardens, you name it. So they find another useful life, which may be even better than recycling.
It's a form of recycling.
Yeah, yeah.
Are people using more water?
You know, interestingly, that was a question. One of the assumptions we had as we were starting was that we needed to collect that data to understand, you know, the households who have access to a water wheel suddenly becoming unsustainable in their water use. But what we found is that it levels off at about 18 liters per day. So people are still not even using the full amount that's absolutely necessary, but it's enough for them to get by.
Okay, Zach, go ahead.
So I have a question for Cynthia, another question for Professor Yaghi. So we'll go with first question. So I was wondering, what was the very first, I would say like the click that makes you, come up with a design for the Wello?
Sure. We tried so many things. I'll just caveat it by saying we really looked at a variety of solutions, and we didn't want to rule anything out too early, even if it sounded silly or crazy. We experimented, for example, with taking balloons, like helium balloons, and putting small amounts of water. We attempted to rig up a rope infrastructure, like a pulley system. We tried flexible pipes, laying those across the ground. I think what the kind of wake-up moment was when we just started hacking apart people's existing containers, and we realized, oh, we can actually just move it in a different way. And there's actually, I have to give credit where credit is due. The original inspiration was the Garangario, which is a rolling water container that it's only found at the border of, I think it's Kenya and Somalia, and it's an incredibly arid region. It's some of the longest distances that people go to collect water, and they'll use used vegetable oil containers, cut them in half, and force them together. It's not perfect, they leak, and then they'll take any sort of wire that they have and rudimentarily create a place where you can tie a rope and pull it. It kind of works, and so that, I had heard about that from someone and thought maybe we could try it with existing containers here in India, and that's really what we were surprised that it would take off, because there were so many reasons why rolling water along the ground should never have worked, but then it did.
Thank you.
Thank
Please
you.
Go ahead.
Hi, I want to ask the speakers the same question Professor Yaghi asked the speakers in the morning, which is, how do you discover? So anybody can answer that.
Jessica, do you want to start?
I'll give the same answer that was given yesterday. It's the surprises. So it's not that you're going out and saying, I'm going to do a discovery. It's you're doing your work. You're trying to ask a question that you already have in mind, and you're working towards that in some way, and oh, that didn't work the way I expected to. But wait, oh, something else instead that's actually even more useful. So the discoveries tend to be surprises. I think in general, we might have an interesting hypothesis that should lead us to something amazing, but the fact is that a lot of times things just continue to surprise us, and I think that's where we should expect to have a discovery.
Yeah, similarly, I would say learn how to ask good questions, which is a skill in and of itself. And for me, it's in applying design thinking strategies. So empathy, curiosity, humility, and just rolling up your sleeves and starting before you're ready.
Yeah, that's a hard question because it's also personality dependent. So I would say one good way to discover is to basically, I mean, I would say you have to do it. You have to start doing something. You can't sit back and plan. You sort of have to go in and start doing something. When you're doing that, whatever it might be, it could be very mundane. Try to dig deep. Try to find things in great detail. Try to keep digging deeper and deeper, and that means asking more and more questions about how things are made up or whatever questions may be. But try to dig deeper and deeper. I'm pretty sure you will discover something because nature is so amazingly rich. That if you approach things in this way, it's probably a sure way of making a discovery. Whether it's a big discovery or not, that's a different matter. But even little discoveries are good because they are the currency of our way of thinking and getting us all excited. So that would be, I would say, one answer that I would give to that question.
Sounds good.
I have one important one to add. Don't be afraid to fail.
That's true. Please go ahead.
Hi, so I have a question for Cynthia, and I was wondering what you see as the next step past the water wheel. So, like, I see a space between the water wheel and having fully formed water infrastructure built, and what do you see filling that space that will really eliminate the time constraint that comes from having to go collect your own water every single day?
Yeah, water from air.
But what about what Jessica has to teach us? Once we know more about where water is and how much there is, then I think we'll have a whole different way of looking at how we access water.
Actually, I have a follow-up. I'm not close to the mic. I have a follow-up question. It's one of these 5-year-old questions. Why is it that a lot of these communities seem to live so far away from their water sources? So we know that historically people tend to build communities near rivers, near lakes, near water bodies, but it seems that these communities are living very far away from them. Is there something to the fact that they've lived there for generations and hydrology has actually changed? Can you talk a little bit about why that's happening?
Yeah, absolutely. So they don't necessarily live far from a water source. So oftentimes there'll be multiple water sources that a village or community will depend on. Depending on the time of the year, your aquifer may just run dry, and you won't have access to that. The well that's tapping into a more shallow groundwater source, and so you have to rely on other sources, maybe a lake, maybe a river, maybe a stream. Conventional wisdom over the years also enables people to understand, well, right after monsoon, I'm not going to go collect water from the lake. Bad idea, potential health risk. I'll go to the river, or I'll rely on rainwater collection. So it's not necessarily that communities live so far, it's that they've developed strategies to deal with varying levels of access over time. And then also, there is, of course, population pressure that adds to this. And, in some situations where I worked in India, there was actually a lot of commercial pollution. There's a lot of the dyeing industry in Rajasthan, for example, has meant that the groundwater is completely polluted. So while people might live very close to a source of water they used for generations, it's so contaminated they can't access it anymore.
Thank you. How about you? Go ahead.
Yeah, hi. I have a question for Professor Yaghi. It's a fantastic talk, lovely work there. My question is, right now you're using heat to get the water out of these structures. Are there other motives that you can build into your structure to use, different functionalities, different stimuli like light or ultrasound or something like that to get this water?
Yeah, the easiest alternative is that since your device is going to be sealed anyway, so that your water the water that you capture doesn't escape back into the air, is to use vacuum, just slight vacuum. Turns out you don't have to pull a lot of vacuum to get the water out. So that's another, I would say that's probably the more economical way of doing it. I like the idea of a stimuli where you have a MOF that, let's say, has two phases. One One is where the pores are shut, and the other one is the pores are open, and you use light or you use pressure or something like that to modulate between the open and the closed system, without necessarily compromising your water, the reversibility, right? This has to be completely reversible. So I like that, and I think Ali may have something approximating that right now, but I don't think it rises to the level of these prototypes. But I think that's a very important direction for our research.
Yeah, thanks.
Yeah.
Thank you. Go ahead.
I have two questions. The first question I have is to Jessica. I was wondering how much work has been done in investigating underground or subsurface water bodies using remote sensing. Yeah, that's the first question.
Thanks, that's a great question. So I very briefly, for maybe a second, talked about that. So most of my presentation was on surface water. There's technology called INSAR, the interferometric SAR, allows us to look at deformations. And so one of the ways that we can one of the ways we can kind of translate that is having an understanding of how aquifers are swelling and decompressing when we're pumping a lot of water out or when the groundwater recharges itself. So we can use this INSAR technology to look at centimeter scale changes in the available water at the groundwater level. In addition to the INSAR technology, there's another technology called GRACE, which again I talked about very briefly, which looks at very, very large scale mass changes. And so basically the way that that works is that it uses two tandem satellites, and they're chasing each other all the way around. And in that chase, one will pull a little bit further forward as the mass of the Earth pulls it, and then the other one will catch up. So all of that difference will kind of give us an estimate of local mass changes. The problem associated with that is that it's fairly coarse resolution. So the map that I showed has a spatial resolution of around 100 kilometers, even up to 300 kilometers, depending on some processing. So the work that I also demonstrated with this downscaling, as well as combining that with INSAR, will give us a better estimate of the groundwater technologies. Additionally, there's more superficially, so in the actual soil moisture layer, we can use the radar technology to penetrate the ground and give us some estimate of how much water is in the soil. But that only goes so deep, it actually doesn't really go beyond about half a meter. So in order to get into the much deeper groundwater levels, we need to get a sense of the large-scale mass changes, which we can do using INSAR or the GRACE instrument.
How about using, let's say, low-level flying UAVs equipped with ground-penetrating radars in that case?
Exactly. So the radar technology is, so the ground-penetrating radars, which would probably be in like the L-band or UHF, P-band spectrum, is what allows us to do this ground-penetrating technology. It still doesn't reach this groundwater table level in most cases. And it's important to consider that the groundwater or the aquifers varies spatially. So the depth of that might be 2 meters in one area, it might be 6 meters in another area. And so the groundwater, the ability to detect and identify where the groundwater is going to be spatially varying. That is, you might be able to do it very well in this area if the water table is up very high, but if it's not, then the signal is going to attenuate before you're able to reach that. But exactly, the UAVs is a technology that people are working on, that I've worked on with my previous lab group as well.
Okay, if you may allow me to ask a second question to Professor Yaghi. I was wondering what's your opinion in maybe other potential water sources that could be accessed using the power of MOF or KOF materials?
Well, I mean, there is a lot of research on cleaning water using KOFs and MOFs. There's a lot of literature on cleaning water from pharmaceuticals and things like that. I mean, also some of the ZIFs, these zeolytic image isolate frameworks, are being used as additives into membranes, desalination membranes and things like that. So, but I am of course, I'm biased towards water from air because it's there and it's pure. It's just a matter of capturing it.
Can I ask, because as you mentioned in your presentation, this offers an autonomy to regions that don't have water access. So how are you already trying to speak to some of these regions that have these problems, because it can potentially avoid huge conflict going forward?
Well, I think in the fullness of time, we will get there. I am a strong believer in technologies that work, and this works. This works. The MOF is scalable. The MOF can be made in water. In my own lab, we make that MOF in water at 20 kilogram scale, just my lab. I mean, we don't do scale up, but we easily can scale this up to 20 kilograms. The Department of Defense is extremely interested in this, and we're working on a device that would generate about 1,000 liters per day. So, and the device, the requirement is that that device can be carried by 3 people. So it can't be heavy, it can't be too big. So, and in my own lab, we are making prototypes that work in the desert. It seems like you've got and the water is pure, the MOF is stable, everything is falling in place for this thing to expand. I think in our societies here in Western world, we get water, we can readily get water. But in the other parts of the world, there is just incredible enthusiasm for this kind of technology. So it's just, I would say it's a matter of time before it reaches there. Obviously, in the beginning, you probably need governments to finance deployment of large, we are part of our vision is to make very large village scale units that deliver 20,000 liters per day.
Have you worked with the United Nations at all on this? Or?
Well, I think this requires a lot of time and dedicated staff to talk to all these stakeholders. But if you're raising money, there are tons of money for this kind of research, for this kind of, let's say, commercialization. For that, and of course, you all know about the CO2 capture. So I'm not worried about this reaching society. I think it's already reaching society, but to answer your question, for those countries, so our techno-economic analysis show that for a family of 4, we can supply enough water, and the cost would be $1 per day, okay? But somebody might have to pay for that device. You can imagine the device is not very expensive because, like I said, 200 grams of MOF give you 5 liters of water. With the LAX MOF, you get 50% more. That's about 7 to 8 liters of water from 200 grams. That MOF stays in the device for 5 to 6 years, actually for the lifetime of the electronics of that device. So everything is looking really good for getting this out there and scaling it into society. Yeah.
Okay. Your question, please.
Yes. Hello. I have a question for Jessica. Can you please share with us some, let's say, observation you observe when you have data on, you use satellite data on Mekong Delta, like water surface, and what should we learn from the data? For example, I was born in Mekong Delta. What should I do when for example, in the future, when I be back to Vietnam, I say to people, stop doing this, stop doing that. You are generating, like more pollutant, or you increase temperature or whatever. So what should I do? So first, what should we learn from the data? And
that's a really excellent question. I would say it depends on what you're looking for. So I really just talked about flood mapping in the Mekong Delta. And so that's really just a question of how much water is there, what is the flood extent. And as you know, perennial flooding in the Mekong Delta is extremely important. You need that for crop health. However, it can get out of control. It can be very dangerous. So a lot of the work that I was doing was to kind of get a better understanding of the true flood extent that can be used to help people who are in danger and who are in crisis. In addition to that, if you are interested in understanding things such as like the water quality or what's actually happening to the water, there's a different assessment that I didn't show here that you can look at the spectral properties of the water, again, very similar to what we've seen throughout this conference where people are looking at the spectra. You can identify different chemical properties that are in the water, different constituents in the water. And so if the people are polluting it, you can detect that fairly reasonably using a lot of remote sensing data. Again, the map that I showed was from a technology called Landsat, or a satellite called Landsat, which is a 30-meter spatial resolution, so those pixels are fairly coarse resolution. But if you want to look at things like floating plastics or trash in the water bodies, there are much higher spatial resolution technologies that have been recently developed that are on the order of 1 meter spatial resolution. The drawback to that is that they're not always very high in temporal resolution, so you don't have like a lot of revisits, but even now we're starting to even counteract that. So there's a lot of modernizing technology that's allowing us to ask a lot of questions that are allowing us to learn a lot more about what's going on in the water. What's also particularly interesting about the Mekong or about the Mekong Basin is that they have a lot of hydropower dams that are being put in as well. So our ability to continually track all of this information, we'll actually be able to see the impacts of those dams and how that's changing the annual flooding cycle. So it depends. It depends on what you're looking for. Again, I just talked about very few satellites that are available. I'm very happy to talk with you about this at length. But there's a lot of different satellites that are going to be able to tell you a lot of very different things about the Mekong Delta. And again, that's one of the things that I really like about remote sensing is that if you have any question about what's happening on Earth, there's some observation for you.
Okay, thank you.
Yeah.
Thank you. Okay, go ahead.
Yeah, two questions and a comment. Jessica, I really appreciate the simplicity of your solution to a kind of complex problem. But because it looked like there's only four parts maybe, the handle, the container, the lid, maybe a gasket. But that container is what, polyethylene, polypropylene? Does it have to be injection molded? I don't know. So is there any possibility of that being made in country so that you spur some kind of business development for that? Clearly the tools that you need to make that are, require some infrastructure, but is there any opportunity there?
Yeah, absolutely. We intentionally tried to make as few moving pieces as possible, keep the design as simple as possible, and we do manufacture in India. So we manufacture locally.
Oh, really? Oh, great. And then my other question was for Professor Yaghi. So the molecules you show are very beautiful and symmetric. The one molecule I didn't see in your list that has that symmetry is adamantane. So has that ever been considered as one of these units?
We have linked adamantane tetracarboxylate and all the expanded, you can add benzyl, 4-benzyls.
Right.
And we've done all of that, and others have as well. Yeah.
Is there any benefit to that? That's because I heard you say diamond structure. Somebody said diamond structure at some point.
Yeah, I mean, I told my students not to touch that anymore because they keep making diamond-based structures, and diamond-based structures like to interpenetrate because diamond is a self-dual,
Sure.
meaning that it can easily interpenetrate. Now, there are some structures like MOF74, the one where we put the proteins in there. That one doesn't interpenetrate because just mathematically it's not possible. It's just, it's not, no matter how large you open that the pores, it's not going to self-interpenetrate because the structure is based on rod units, rod SBUs. Or rod.
So that's you're going for the rod structure.
Well, it looks very interesting. The rod structures seem to have come out on top so far for carbon capture and for water harvesting, but I can't say that there's the reason they're special, let's say, for water harvesting is that they that rod arrangement allows you to hinder the aluminum-oxygen bond, and that's why they're very stable in water. They shouldn't be stable in water. Aluminum-based MOFs generally are sensitive to water. They can hydrolyze. But if that aluminum-oxygen bond is not accessible to water, then you're safe.
Okay.
Then it's eternally stable, right?
Right, okay, thank you.
On the time scale of what you want the device to function, yeah.
Thank you very much. Okay, you have a question?
Yeah, a quick question for Cynthia, just out of curiosity. Coming into these local, sometimes remote areas, was it difficult? Did you receive any pushback from locals when you come in with your idea? You're like, oh, this works. But how do you convince someone coming in, different culture, and just being like, hey, be convinced?
Sure. So my guiding philosophy always, and this goes back, I studied anthropology in undergrad and did field work then, was always receive an invitation. Don't ever go anywhere you're not invited. So when I initially started work in India, I knew nothing. I literally just looked at a map and said, oh, there's a desert, probably a good place to start, and set out to basically make friends. So I got to know some other organizations who are working on a variety of different water issues, education issues, women and girls empowerment, and I asked if I could shadow them, and I asked if I could learn about their work, learn about the challenges, and shadow their field staff as they went on trips into the village. Later on, I also volunteered for a company called Sarvajal, which was a reverse osmosis kiosk system that was providing community-level water. Volunteered to go help their technicians. So I started making a lot of connections and hinted to anyone who would listen to me that if someone was open to having me stay in their home for a week, I would be very happy to do that, and eventually got an invitation. And once I got that first invitation, the invitations started flooding in. So I had kind of a list of visits I needed to make, and I got to know a lot of about water conditions in a lot of different villages, and that was really, it was kind of a snowball effect. So it took a while, but I feel like I had to be patient with it, and eventually those connections opened up.
So it sounds it's pretty much about like only word of mouth. Once one person trusts you, others follow until it spreads. Do you think, compared to if you would have had a similar idea or a different idea, implementing it, let's say, in the US, is that more difficult or less difficult to convince people, or just different?
It's hard to say. So I personally haven't done community level work in the same way in the US, but I'm thinking about a friend who so it's a organization who I partnered with on figuring out some aspects of the water wheel design. They also did some work on water on Native American reservations. And even though the founder of the organization was Native American, she said she had a really hard time using that approach and getting an invitation. So they actually ended up doing a series of year-long workshops just to build trust in the community. So I would say it's a similar approach, but the time scales might be different. And I would say don't make assumptions that because you think you have a connection, that your perceived connection is also perceived as a connection from the other side, and just find those areas where there is that inflection point, right, where you do have something in common and you can kind of build that trust together.
Perfect, thank you.
Yeah.
So looks like one more question.
So first, I would like to thank for all your presentations. I have a question for Jessica. So it's very interesting to see that you can get so much information from all these beautiful techniques. And I'm wondering, would these techniques be able to differentiate the signals from water versus like ice or snow? Because for many great rivers on the earth, they originate from the summit of the mountains where the summit are covered by the snow. So in those places, the snow and the water are in the phase equilibrium. So they are all very cold. So in those situations, would your satellites be able to differentiate the signals?
Yes, so there's a few different things that we can look at. So you can look at it from an optical perspective, that is, it looks different. So the snow or the ice may or may not look different from the water. So I've done this with previous research on melt ponds. So you have melting on the surface, but you have ice or snow underneath, and so those look optically different. So again, if you were standing there and you looked at it, you could tell they look different. But you can also use the radar data. So you can use the dielectric constant of the water, and you can basically be able to understand that these are different structures. So the same thing that we've been talking about with the water structure. So you can identify the difference between the liquid and the liquid and solid phase of the water body using different radar techniques. I think most of the examples that I've seen use a longer wavelength radar, but I imagine it should still be, that is just because the shorter wavelength radar, such as from SWAT, we don't really have any observations to kind of confirm that, but theoretically this is also true. So with radar techniques, you can observe the different phase of the water, and with optical techniques, you can observe the color and the shape and the structure. So again, it just depends on what you're looking for, but there's a lot of different technologies that enable that.
Okay, thank you.
Thank you. So again, I want to thank our speakers from this afternoon, and Professor Norden, if you want to say anything from Molecular Frontiers to close out the conference, please do.
I might have some questions for you. If I start with you, Jessica, look, we are covering a very important problem, a very complex problem area, where we go from microscopic levels, understanding mechanisms in protein and life processes at the molecular level, all the way to the water demands in the future that we will have. And if I start with you, Jessica, we, even if we in the long run may mitigate the undesirable climate change we have, I think we have to live with the rather pessimistic prognosis that the temperature will increase, and with that land ice, Antarctic land ice, and also Greenland may melt, and that will raise the sea levels. So one way of solving that, this hypothetical way, would be to increase the number of stored water, fresh water in reservoirs all over the world. I made a back of the envelope calculation on how much we need to compensate the next 20 years melting, and I came up with 1 million reasonably big reservoirs. So my question to you is it possible to think ahead and be a little proactive, knowing how to document the precipitation we have and the distribution, and so we could start early to build these reservoirs, which then will help also to those who lack fresh water today. Have you any ideas about that?
That's a really interesting question. I haven't really considered that, so I'm going to give you a bad answer. To the question of accounting, I think you're absolutely right. That is, we can just keep monitoring how much precipitation is falling. Technically, if you think about it from a precipitation perspective, from a relative humidity perspective, you can start capturing water before it gets to the sea, such that there's no sea level rise, right? You continue to capture it, and you capture it inland. That theoretically would make sense, and we do have the data to kind of support how much water there is in any given region. So we have an understanding of what are the climate cycles, and again, Dr. Yaghi showed like there's some specific climate regions where you can expect to see that there's a lot of precipitation following every month. So that might be that in areas like Canada, for example, where there's already millions of water bodies, you might have new areas that look like Canada. So I'm just kind of following along with your hypothetical of just having a ton of new water bodies. it's still kind of a question of like, how does that really change the water cycle? So we already know that there's going to be significant changes. If we say that everything will melt, that's already going to be a significant change. But now what are the new changes that are going to result as the impact of just having water where there used to not be water before? So now you have a new evapotranspiration cycle. So we might need to do new simulations for if there is a water body here now, and that water body stores this much water, and the wind speed is this much. So we think about all of these different factors that control evaporation rates, that also might control new vegetation, new species migration as a result of the new water bodies. So all of these things, not too surprising, are all interconnected. So, but we have to think about that. So anytime someone says anything that's hypothetical, I'm like, okay, well, I'll play along. We can see how we'll do that. But there are a lot of things to kind of consider. What's nice about remote sensing combined with modeling is that we can start to kind of play around with these numbers and say, if there's a water body here, what will happen? If there's new vegetation here, what will happen? So I think you're spot on. We do have the capability to do these kind of simulations.
And we might also have a driving force, a political driving force, since everybody wants to avoid being drowned.
You're talking about damming the water, right?
Yeah.
Well, you still have to reckon with all the carbon that comes out of melting of the ice that causes the ocean. Yeah.
So, Cynthia, what you address is the semi-macroscopic transport of water in, what shall I say, a poor citizen context, which is extremely important. And I think one should somehow combine the insight we have on the macroscopic mesh level and the need on the microscopic level. And when we come to the solutions, how to extract the water in dry environment, you are not going to use your MOFs when it's raining every day. That's not the places, I guess.
I want to make the point that the MOF works not just in the dry environment, but also in the humidified environment where there may be lots of water, but it's not clean. It works there very well. And I think that that's actually more exciting application. Somebody mentioned that in Singapore or some other cities, one is able to recycle bathroom water and use it for drinking.
I know some of these projects.
Yes, so that I think that they would prefer to have a water harvesting device in their kitchen where they can control their own water coming from the air rather than from their toilet. So there is a psychological impact there. But
is it a luxury? I mean, how expensive will the MOFs be in a longer perspective? I guess you...
Is this a luxury?
Yeah. Okay, that's the answer.
But you said it's all over, even in the least developed places.
The difference between wants and needs.
Yeah. So I think if you need it, it will develop in that direction. But I'm not saying that this thing is going to be cheap from day one. But what is cheap from day one? And these things get better and better and better. Even before we release our first product, we have increased the uptake of water and the productivity by 50% by just adding 2 carbon atoms to that linker. That's the power of chemistry, I think, is that now what may be not so economical becomes economical because you're delivering 50% more water. So that's these are the things. The device is a complex system that relies not just on the MOF, but also the amount of water in the air, the uptake and release kinetics, speed of the air, a lot of factors that make for an efficient system. But yeah, is the first device going to be for $5? No. Is it going to be $100 for your kitchen? Very likely it won't exceed that, right?
Okay.
So it's not unreasonable.
Just have a quick comment on that related to the cost of the device. 'Cause I found it really very interesting because you noted that a family of 4 might have a device that's around $1 per day. And I guess from like development literature, we know that a lot of families live on around $1 to $2 per day. So that's all of the money that they have. However, what you also pointed out is that this is still a scaling, this is still it's still a process. So it might end up being 50 cents per day or 25 cents per day as things continue to scale up. And from the community's perspective, that maybe it's not a household thing, but that the community is having, you know, a water portal.
Yeah, like I said, I think when when certain things are optimized, I mean, that number is based on 10,000 units. But if it's 100,000 units or 1 million units, the price will be very different, much more affordable. When these guys get back to the lab and start working on that LAX linker and increase instead of 50%, 100%, now my cost is cut by half. So I believe in the power of chemistry, and there is just nothing out there that allows you to change the battleground, the strategy, is that you will be at a different level of solving a problem once you make an invention. So I don't like this, sometimes the extrapolation, because the extrapolation doesn't take into account the brilliance of the people that are doing the research and the fact that there are discoveries. So I think we should be cautious about extrapolating based on what we know today.
Moore's law, for instance, and the cost today of a very powerful computer. That could not have been extrapolated.
Yes.
Back to Chief Moderator.
So I was giving you the floor to say goodbye from Molecular Frontiers, but will you do that, or should I say goodbye?
You could say it.
Goodbye, and thank you very much.
Okay.